Okay, I think we're ready. So, hi everyone, and welcome to the third week of the 32nd International Conference on Formal Power Series and Algebraic Combinatorics. My name is Angela Carnevale, and I'll be moderating today. Today, we have three speakers. Each talk is 25 minutes long, with 5 minutes in between for questions and a short break. And we will also host a special event in 2 hours from now, so at 4 UTC, we will host a memorial tribute to Rowan Graham. There will be a short coffee break between the last talk and the memorial, so please stick around and everyone is welcome to participate to the whole session. The chat monitor for today is Arvind Iyer. And so I think we are ready to introduce our first speaker. So our first speaker today is Ilse Fischer from the University of Vienna, and she will be talking on the first bijective proof of the ASM theorems. So Ilse, take it away.
Thank you. So hello to everybody from Vienna. So I'm talking about first bijective proofs of alternating sign matrix theorems. This is a joint work with Matjaž Konvalinka. So here is a short outline of my talk. So there will be 3 parts. So first there will be an introduction. I will define all the objects. I will talk about bijection 1 and bijection 2. Then I will tell you briefly what are sign sets and what are bijections. And then I will give some details on our constructions. So let's start with the introduction. An alternating sign matrix is a square matrix with entries 0 plus or minus 1, such that in each row and each column 2 conditions are fulfilled. So first of all, the non-zero entries appear with alternating signs. And the second is that the sum of entries is 1. So if you look at examples, so first of all permutation matrices are of course alternating sign matrices. And for order 3, there's the first non-permutation matrix that is also an alternating sign matrix, which has a -1 in the center. So it's known that alternating sign matrices of fixed size are counted by a simple product formula, as I've written it here. So the second objects I need to define are descending plane partitions. So for that, you need to know what is a strict partition. A strict partition is simply a partition with distinct parts. And if you have such a strict partition, you can have a shifted Young diagram, where you have in row I, you have lambda I cells, and you have a staircase on the left side. And then you can fill in numbers, and you want to fill in numbers in such a way that rows decrease weakly and columns decrease strictly. And this is why we call them column strict shifted plane partitions. But I need 2 more conditions. So the first one is that the first part in each row needs to be greater than the length of its row. And also this first part has to be less than or equal to the length of the previous row. And now you might wonder, well, this is an ugly condition, but this is actually precisely, conditions are precisely good for the fact that these objects are in bijection with certain lozenge-teilings, as I've drawn one example here. So these are cyclically symmetric lozenge-teilings of a hexagon, where you have a triangular hole of size 2 in the center. So next, I've listed all descending plane partitions with parts no greater than 3. So they are here. And as you can see, there are 7 of them. And we also had 7 alternating sign matrices of order 3. And that's not a coincidence, because Andrews showed that the number of descending plane partitions with parts no greater than n is actually counted by the same formula as alternating sign matrices. Okay, so now I tell you what our first bijection does. And for that, I need to define a bunch of sets. So first of all, ASM sub n is just this set of all n times n alternating sign matrices. And then I is an additional parameter. So that's the position of the unique 1 in the top row of the ASM. So one can show that an ASM always has a unique 1 in the top row. Then the next two sets are of a simpler nature. So Bn is the subset, is the set of all 2n minus 1 subsets of a 3n minus 2 set. And these sets can easily be counted. So that's of course given by a binomial coefficient. Then we also consider refinement where we fix the median. And here we get a product of two binomial coefficients if we count the number of elements. And then finally, I also need descending plane partitions with parts no greater than n. And our first bijection is a bijection between these two Cartesian products. And the important thing to note is that this refinement parameter moves from ASMs to this much easier set B. And of course, if we have such a bijection, we can simply take the union over all I, and then we remove this refinement parameter, and we have this bijection here. And now you see that we have a recursive nature. So here we have ASMs of order n, and here of n minus 1. So we can iterate this and finally obtain such a bijection. And then if we take cardinalities, then the TPPs will be cancelled. The B's we can easily count, and then we can simply read off what the number of ASMs is of order n. So here's an example. So our bijections are far from being easy. So therefore we have coded everything, and here is the particular example for n is equal to 3 and I is equal to 2. So you see that a triple of certain objects is mapped to another triple, and the order of the alternating sign matrix has decreased by 1. Then bijection 2 is one. So I should say that bijection 1 is the one that gives a bijective proof of the product formula. Bijection 2 explains the relation between ASMs and descending plane partitions. And actually we can do a refined enumeration of descending plane partitions. So we fix the occurrences of n. So we have I minus 1 occurrences of n. And then we have this bijection between between two Cartesian products. So here we move the refinement parameter from the ASMs to the TPPs. Then if we take cardinalities, we get this relation here. By induction, we can assume that the order n minus 1 objects have the same cardinality. From that, we can conclude that the refined enumeration is the same. And then again, we can sum over all I and get the result for order n objects. And again, we have also coded this. So this is now very tiny. But it transforms a pair into another pair. And here we have chosen n is equal to 4 and I is equal to 2. Okay, so now we move to the second part. So I want to show you how we really constructed these bijections. So first I need to tell you a little bit about sign sets. So a sign set is always a pair. So a sign set is when you divide the set into a positive and to a negative part such that there is no overlap. Then the size of a sign set is always the difference between the cardinality of the positive part and the negative part. Then the opposite sign set is the one you obtain by interchanging positive and negative part. Then you can have Cartesian product. So what you do is you take the Cartesian product of the positive part and the Cartesian product of the negative part for the positive part, and for the negative part, you take once the positive part and once the negative part. Then you can have disjoint union. So what you do is you just add a coordinate to make all elements distinct. And even more important is that we can have a disjoint union of a family of sign set. And note here that the indexing set actually is also a sign set. So these are constructions that we will need for our purpose. And now I think it's time to explain you our approach. So why do we need all these definitions? So the thing is that we translated some of my non-bijective proofs into combinatorics, and note that the disjoint union in a sense models the addition. Having signed set allows us to deal with signs, and this Cartesian product allows us to deal with multiplication. So we can deal with all arithmetic operations except for division. And this should now also explain why we had these redundant factors. You remember in the first bijection I had descending plane partition, but the first bijection was just about proving the product formula. So it's really because there is not a really good way to deal with division. This is why we have these additional factors. Then I should say that, of course, in the original proof, signs are unavoidable. And this is why we need to work with sign sets. And here are two questions that I find interesting. So of course, it would be interesting to find a non-bijective proof that avoids signs, because then this can probably translate it into a bijective proof without sign set. Yeah. So next I give you an example of a sign set, which is very important for us. So these are signed intervals. So if the one endpoint, so if A is less than B, it's just an ordinary interval you put into the positive part of the sign set. But if the endpoints are not in the right order, you put something into the negative part, you interchange the order of A and B, you add 1 to B, and you subtract 1 from A. So this is how you get signed intervals. So why are they important for us? So in our construction, we will often have Cartesian products of signed intervals, so signed boxes, and disjoint union of such signed boxes. So next I need to tell you what are bijections. So bijections will play the role of what bijections play for ordinary sets. So bijections should show that the sizes of the two sign sets are actually the same. So here is the definition. So a bijection is always an involution on the disjoint union of the elements of the two sets, such that elements from S plus and from T minus are mapped to elements from S minus or T plus. So another way of thinking about this is that you actually have three maps. So you have a sign reversing involution on a subset of S, and this is indicated with this blue part here. Then second, you have a sign reversing involution on the set T, so that's indicated with the green part of it. And for the rest, you have a sign preserving bijection from the remaining part of S, which is gray here, to the remaining part.
It's recorded.
Part of T.
I'll tell you about it.
And of course, this implies that, that the sizes of the two sign sets are actually the same. So that's what we will need. So here I show you a very easy bijection, which is again actually the building block for many of our bijections. So here you now have three integers. And I claim that there is a bijection from the interval AC to the disjoint union AB, B plus 1C. And now you have to distinguish cases in order to construct this bijection according to the relative positions of A, B, and C. So if A is less than or equal to B or less than or equal to C, then the two intervals on the right side are actually disjoint, so there's nothing to do. But if you have this order here, so A is less than or equal to C and C is less than B, then this picture explains everything, because you see that the interval AB is actually the biggest interval. Then the green interval is actually a negative interval because the endpoints are not in the right order. And so to speak, these green elements cancel some elements from the purple interval, and what remains is the yellow interval, which is just the interval on the right, on the left side. So this is the idea of this bijection, and it works the same for all the remaining cases. So this is now a slide you shouldn't really read now. So what it should show you is that one can also have a notion of Cartesian product of bijections and disjoint union of bijection. So you take this fundamental bijection we had, and then you take certain Cartesian products and certain disjoint union of this Cartesian product, and you get more complicated bijections. And this is the nature of the bijections we usually have. So I want to spend a little more time on the composition of bijection, but I also will not show everything here. So we want to construct a bijection from one set to the other. And actually this bijection will be a composition of many bijections. And in order for this to work, we need to have a notion of composition of bijections. And there actually is such a notion, and this picture explains it. So we have a bijection from S to T and from T to U. And then by alternating applications of phi and psi, you can actually construct such a composition. So let's look at one example here. So in this picture, there are several cases. So from S plus, we go to T plus via phi. Then we go via psi from T plus to T minus, and we do this several times until finally we reach U plus. And actually that's nothing new, so that is known for a long time. So the case where S minus and U minus is the empty set, that's precisely the Garcia-Milne involution principle. Okay. So I can finally give you some details on our constructions. So we are interested in alternating sign matrices. And first, it's helpful to translate everything into monotone triangles. And this slide should explain how to do this, so that's well known. So here we have an alternating sign matrix. And from that, we construct a 0, 1 matrix. And how we do this is that we add to each entry, we add every entry that is in the same column above. So to this entry here, to this 0, we add everything that is above, and this will give us a 1. And we do this for every entry. And so that way we will obtain a 0, 1 matrix that has 1, 1 in the first row, 2 1s in the second row, and so on. And from that, we construct a triangular array, and we simply record the positions of the ones. So in the first row, we have a 1 in the second column, then we have a 1 in the first and the fourth column, and so on. And that way, we can always construct such a triangular array. And if you think a bit about it, you will see that this array is always weakly increasing in northeast direction and weakly increasing in southeast direction. And in addition, it is strictly increasing along rows. And now I introduce a notation for this monotone triangle. So by MT, and then we write down the bottom row. So in that particular case, K1 is 1, K2 is 2, and K3 is 3, and so on. We get this set of monotone triangles with a prescribed bottom row. So if we drop the condition of the strict increase along row, we still have arrays that are weakly increasing along rows, because that follows from the other condition, because here we have a weak increase, here we have a weak increase, so then we also have here a weak increase. But if we drop this condition, then these objects are also well known. So these are Gelfand-Zetlin patterns. And they are also important for our construction. And what is important is actually that we have a notion of Gelfand-Zetlin patterns with arbitrary bottom rows. So far on the previous slide, I've only defined them for weakly increasing bottom row, but we need this for every integer bottom row. And this is also where signed intervals, for instance, come into the play. So here the condition is that each entry has to be in the interval of its southwest neighbor and southeast neighbor. So for each entry that is not in the bottom row, it has to be in this signed interval. That's the condition for arbitrary bottom rows. We want to make this into a sign set. So how do we assign a sign to this object? Well, whenever we have two adjacent elements that are not in the right order, so two adjacent elements in the same row that are not in the right order, so which means that the left entry is greater than the right entry, then this contributes a -1 to the sign. So that way we get the sign. Then I denote this sign set by GT, and one can actually show that the signed enumeration of these Gelfand-Zetlin patterns is given by this product formula. So that's actually a rewriting of the hook content formula, because Gelfand-Zetlin patterns are in bijection with semi-standard tableau. Okay, so then I need one other object. I need arrow patterns. So these are again triangular arrays, but much simpler this time. So I allow three types of arrows. So I have these two arrows, and then I have this double arrow. Again, I want to make this into a sign set. And now these double arrows contribute a -1 whenever it appears. And we finally get the sign set of arrow patterns. We denote it by APN. So why do we need these arrow patterns? Well, these arrow patterns induce the deformation of the bottom row. So they induce the deformation of the Ki's, and I've given an example here. So here you see an arrow pattern, and at the bottom I write down K1, K2, K3, and so on. And then I subtract and add some numbers. And what I subtract is the number of arrows that are pointing towards the entry in this diagonal. And what I add is the number of arrows that point towards this entry in this diagonal. And then I get some integer added or subtracted to this Ki. And so this will give us some deformation of this n-tuple, K1, K2 up to Kn. And now with these two objects, I have defined Gelfand-Zetlin patterns, and these arrow patterns, I can define shifted Gelfand-Zetlin patterns. So they are a disjoint union over all arrow patterns. Then I take the deformation of these, the deformation that comes from the arrow patterns of the bottom row, and then I take all Gelfand-Zetlin patterns. And now you might wonder, so why do I need this shifted Gelfand-Zetlin pattern? So actually the thing that is very helpful for us is that we could construct the bijection from monotone triangles to this shifted Gelfand-Zetlin pattern. So this is all our construction underlying is this bijection, because it turns out that these shifted Gelfand-Zetlin patterns are easier to deal with. So this is also what I wrote down here. So the merit of this bijection is that from now on, we can always replace monotone triangles with shifted Gelfand-Zetlin patterns. So also this is coded. So here I give the example when the bottom row is 1, 2, 3. So here you have a monotone triangle where the bottom row is 1, 2, 3. And the bijection maps it to a pair of a Gelfand-Zetlin pattern and an arrow pattern. So, I skip a lot of details, of course, I cannot do everything, but this bijection between shifted Gelfand-Zetlin patterns and monotone triangles, that's one crucial thing. The other crucial thing is a bijection that shows this relation here. So a bijection that transfers a monotone triangle with this bottom row into a monotone triangle where I've moved the first coordinate to the last position and subtracted n, and then depending on the parity of n, I also have a sign. And so we did what I just said on the previous slide. So instead of showing this for monotone triangles, we actually showed this for shifted Gelfand-Zetlin patterns, and then using our bijection to monotone triangles, we also have such a bijection for monotone triangles if we use decomposition. So these were the two important things about the bijections, and then after many more steps, one finally obtains these bijections 1 and bijections 2 I've indicated at the beginning of my talk. So I think I need to stop here.
Thanks, Ilse, for this great talk. And if you unshare your screen, we can all share our reactions. And I think there's quite a few questions in the chat, so I'll pass it on to Arvind.
Okay, so thanks, Ilse. So there have been quite a few questions. Some of them have been answered. Dan Betia asks, just one second. Yeah, here it is. So can the construction, I presume he means the bijection construction, can the construction be extended to accommodate spectral xi, yj, and q parameters on the ASM side?
Can you repeat this? I didn't get this.
He says, you know, in the ASM picture, we have these spectral parameters, these xi, yj's, and these q. So I think he's asking if the construction can be extended to accommodate these parameters.
Actually, I haven't thought about this. So that would be some weight preserving. I don't know, possibly. Good question.
Okay, thank you. Art Duval asks, can bijections be used to explain more neatly counting formulas that previously required inclusion-exclusion?
I don't know. I don't know of any example, possibly.
So Bruce Sagan answered that since inclusion-exclusion can be proved just with a sign reversing involution, in some sense you just need such involutions, not the full power of bijections. Do you agree with that?
I think so, yes.
Okay, perfect. Okay. Sam Hopkins asks, do GT patterns for bottom rows that are not partitions have some meaning in terms of Lie algebra representation theory?
Actually, I don't know. Would be good to know. I don't know anything.
Okay. A couple of more questions have come up. François Bergeron asks, he makes the remark that for any representation R of Sn, it should be possible to describe R as a signed set representation. However, one would like nice such descriptions.
Mm-hmm. Thank you.
Okay, Soichi Okada asks, does bijection 2 preserve certain statistics or commute with operations of DPP/ASMs?
I mean, we have this one additional statistic on ASMs and on descending plane partitions. Apart from that, we haven't seen anything. So I would say no at this point.
Okay. And Cyril Bonterier asks, is there any remarkable properties of lower triangular alternating sign matrices? I guess.
Of lower triangular alternating sign matrix. I mean, these are, this could refer to symmetry classes of alternating sign matrices. And yes, I mean for diagonally symmetric alternating sign matrices, there is no nice formula. So that's probably not so remarkable. but it's
Yeah,
also
but
true.
you can't have alternating sign matrices with entries purely below the diagonal, right? You have to have some, I mean, the worst case would be the identity matrix. Right? I mean, you can't have things only below.
Yeah. I mean, what would this, so you mean on one half there are only zeros?
I think that's what he means. I'm not sure, yeah.
Which means that you have, well, I don't know. I would have to think a little bit. It's a lot of questions. It's being exhausting.
Okay, thank you, Ilse. Back to you,
Okay.
Angela.
Well, thanks, Ilse, again for your talk. And